In order to land things on Mars, we need to slow them down before they hit the surface. We use the Martian atmosphere to do that, but the Martian atmosphere is very, very thin. It's only 1% as thick as Earth's atmosphere. So these decelerators have to go out at very high speeds at Mars, at supersonic speed. And they have to be very large to slow the vehicle even down to speeds of a couple hundred miles an hour.
So what we have are an inflatable aerodynamic decelerator. That's the soft goods, this yellow textile article that you see on the side. And what will happen is that this will inflate very rapidly in a fraction of a second, about a third of a second, and it will increase the size of the aeroshell, and it will create a surface much larger than the vehicle alone, with which we can react against the atmosphere and generate more drag and slow the vehicle down further.
What we have out at a test range off of Hawaii is an ability for the infrastructure to be able to do this testing safely, effectively, and efficiently.
In the background here we have our launch tower. We launch a large scientific balloon, a 34 million cubic foot helium balloon that carries our 7,000-pound test vehicle up to 120,000 feet in the atmosphere. That vehicle has on it a large rocket motor, which then fires and takes the vehicle even higher, up to 160 to 180,000 feet, where the atmosphere is like it is at Mars, where we'd use these decelerators. And then it's going about sideways. We deploy at Mach 4 our first decelerator, what's called our SIAD, our supersonic inflatable aerodynamic decelerator. It's a large tube that inflates around the vehicle. That slows it down to Mach 2.5. And at Mach 2.5, we deploy a large 30-meter parachute. Those are the two technologies that we're testing. This is a shakeout test to see if we can get the vehicle up to the proper conditions. If the vehicle goes off course, or if it doesn't reach the trajectory that we want, or if we don't get the conditions we want, or if the cameras aren't working, or any of those things, those are exactly what we're looking for to learn what happens, take that information, incorporate it into the next two flights that we have next year.
Some would argue in technology development that if you don't push the boundary a little bit, you will never learn. So we have to take the right amount of risk. We do the right calculations, we do good engineering, but we are pushing the boundaries of these technologies.
So my boss told me that if this thing works perfectly, if it does exactly what we expected it to do, it exactly hits the targets that we want, it flies the way we want, it gets the data back exactly like we want, all the cameras work, all of that, then I get an A. But if we have some failures, if we have some problems, if we see things that we learn from, that we can apply to the next flight, then I get an A+.